Mesdames, Messieurs, bonsoir.
Good evening, ladies and gentlemen. Welcome to the last evening of the 18th Reich Colloquium 2018. I must say it's quite extraordinary to see so many people in the room, and I think that we're about to open another room to take in everyone, which is quite unexpected on a Friday evening, and we have lots of young faces in the audience, and hopefully they have the possibility of putting questions. So this evening, you know, we're going to welcome one of the most prestigious scientists. He was awarded last year the Breakthrough Prize, which is not yet as famous as the Nobel Prize, but it goes with a hefty check. So it's a very interesting prize to be given. So Professor Strominger is going to take us on the road to gravity and gravitation. As you know, it's a topic for this year's colloquium. He's going to go over everything that has been discussed this week, and he's going to talk about gravity, general relativity, and quantum physics. Most important topics in physics which we're trying to link, and that is in fact the holy grail for modern physicists. I'm going to leave that scientific presentation at that for the time being. Now, as you are well familiar with the system, don't switch off your cell phone, just switch it on to silent mode. Unfortunately, we still hear a few ringing tones every evening, so switch it on to silent and use Twitter, because Twitter is a way which will allow you to put questions. You can put questions in French or in English on Twitter, and they will be repeated on the rostrum during the Q&A session just after this evening's conference. So before we get down to business, I'm going to give the floor to Thierry Courvoisier, the president of the Wright Foundation, who is also going to say a few words of welcome. You have the floor, sir.
Bonsoir.
Good evening. After having spent a week listening to a number of conferences on gravitation, this force that is so familiar to us, which stops us from climbing hills as fast as we would like to, some would believe, probably, no doubt rightly, that we could have come up with solutions and answers to all the questions we may have about gravity, but that's far from being the case, as you will have understood by now. This evening, again, we are going to be left with a question, not really an answer. Gravitation was developed as a classical theory, i.e. a theory which is not quantified. It's not a quantum theory. It's not a field theory in that sense of the word, whereas all the other forces of nature for some time now have been consistently described in quantum fashion. All the efforts in this area have remained unsatisfactory when it comes to gravitation. Now, this is not because we cannot find the answers that we shouldn't try and throw light on the question, especially if the question is well put and has been well put for many decades, and if we have partial explanations, which is the case when you look at the quantum aspects of gravitation. The Wright Foundation is very happy indeed to have with us Andrew Strominger this evening, because he's going to talk about this particular chapter this evening to all you people here in Geneva.
Voilà, vous le savez certainement.
So, as per usual, we'll have our university professor to introduce this evening's speaker. So, without further ado, I shall give the floor to Marcus Marini. Marcus Marino, my mistake.
Nice to introduce for you Andrew Strominger. Andrew Strominger is a very distinguished scholar. He is a professor of physics at Harvard University, where he is also the director of the Center for the Fundamental Laws of Nature. As we have already heard, he has obtained numerous important prizes, including the Dirac Medal, the Klein Medal, the Heinemann Prize, and the Physics Frontier Breakthrough. Andy is really a remarkable scientist. His research encompasses an amazing variety of topics. For example, closer to my research interests, Andy has done a very important and fundamental work in mathematical physics, and he has made a lasting impact, for example, in modern geometry. But the true leitmotif of Andy's work is definitely gravity, and that's why he's here today, and that's why we are here today to hear his talk. Now, Andy, as the other speakers have already reminded us, has focused on one of the most important problems of modern science. And this problem is the following. How do you put together in a consistent framework the two modern pillars of physics, which are general relativity of Einstein on one hand and quantum mechanics on the other hand? And I remember that in a talk that Andy gave in China some years ago, he was putting this problem in very telling terms, and he was saying the following. Now, the students of physics take courses in quantum mechanics on one hand, and they take courses on general relativity on the other hand. But these two courses, if you look closely at them, are actually incompatible. And we have to address this problem in some way or another. So Andy has actually attacked this problem with a lot of imagination, a lot of energy, and using essentially all the kind of tools that theorists have at their disposition. And what's more important, he has attacked these problems with a lot of success. Now, for example, a very important result of Andy, together with Cameron Buffa, is that he provided the first microscopic description of black hole entropy. I'm sure he's going to tell us today about this, but this was really the first time somebody was able to explain the quantum nature of a black hole. And he actually went on to give quantum descriptions of many types of black holes, including some black holes which are accessible to astrophysical observations. So some of the consequences of Andy's theories could actually be measured in the not so long future. Now, Andy has also given very important insights on one of the most important puzzles of black hole physics. Namely, do black holes destroy information? Are they actually compatible with quantum mechanics or not? And he's probably going to tell us today about this. And this is a problem in which he actually joined forces with Steve Hawking. And some of the last papers of Steve Hawking were actually made in collaboration with Andy to address this very important problem. Now, last but not least, I want to say that Andy is a remarkable human being. He's a true global intellectual. He has an infinite curiosity for all aspects of life and all aspects of science, and I have been really honored to be one of his many collaborators, and more importantly, I have been honored to be one of his friends. Thank you very much. Andy, please.
Well, I've also been honored to be Marcos's friends over many years. It's an honor for me to be here giving this Wright colloquium, and a great pleasure. And I'm going to be talking today about some things that we don't understand, but more importantly, some things that we do understand, but more importantly, the things that we don't understand. And let me give you a brief outline. So I'm going to start by talking in rather general terms about what it means to try to understand nature at its most fundamental level. And then I'll move on to what I view as probably the essence of what it is that we don't understand about nature, and that is black holes and gravity. So this whole colloquium series is devoted to understanding the edge of to explaining the edge of what we now understand, and going on from that to understanding new things. And that is Hawking's black hole information paradox. I'll talk about how string theory ties into this, and then I'll talk about what Marcos was alluding to at the end of his comments, what is going on right now as we speak in trying to make progress on these issues. Now, the problem of understanding the fundamental laws of nature at their deepest level has been going on for many centuries. And in this lecture, I will talk about the edges of what we understand now, which happen to coincide with the edges of the visible universe, the edges of black holes, the things that we can't see far away in our universe. So first of all, though, I'd like to say that it's really, if you stop and think about it for a moment, it's kind of astonishing how much we do understand about the universe around us. You know, we understand how it is that the pasta I had for lunch has been metabolized and has been turned into the energy that is now enabling me to stand here and speak. We understand that we can aim a rocket ship at Mars. We can predict that it will get there to within the, after orbiting around, being deflected by planets and so on, that it will, the exact second at which it will arrive there. Incredibly, last night we heard about how at the LIGO collaboration, they measure the distance between two mirrors 4 kilometers apart to within a tiny fraction of the size of a proton. That's crazy. We understand a lot of stuff in really a lot of detail. At the same time, there's huge things that we don't understand. A 3-year-old can ask us questions. How did the universe begin? I don't know. There's all kinds of things about our universe that are just completely incomprehensible to us. So it's a very strange and exciting situation that we find ourselves in. Now, when we want to learn something new, our friend is a puzzle. Our friend is a contradiction. So one of the most famous of these was more than 100 years ago when Einstein asked himself, what would happen if I held a mirror in front of my face, looked at my image, and kept running faster and faster until I went faster than the speed of light? And there were 2 different theories at the time for predicting that. One was the Newton-Galileo theories of motion, and the other was the Maxwell equations. And they gave different answers. They contradicted one another. One said that the image would just disappear because the light couldn't get there and back, and the other said that the image would just stay the same. So that was a contradiction in the laws of physics that were understood in 1905. And resolving that contradiction, though who really cares what happens if you hold a mirror and run faster than the speed of light? Resolving that contradiction, because it really was a contradiction, not a technical point, resolving that contradiction led to a completely fundamental reorganization of the way we think about space and time. In fact, it taught us, according to Einstein's special theory of relativity, that space and time are really the same thing and can sort of morph into one another, and that can be characterized by saying that nothing can travel faster than light. And this is not an isolated incident in the history of physics. Every single major advance in the history of physics, I won't go through all these. Does this have a laser? Yeah, I won't go through all these, but every single major development in the history of physics had some great body of knowledge that it contradicted, which led, for example, electromagnetism and the laws of thermodynamics and statistical mechanics were inconsistent because if you have a continuous field like the electromagnetic field, you can't count it. To do statistical mechanics, you have to count things. Electromagnetic field varies continuously. You can't count how many configurations there are. And resolving that led to the theory of the quantum. Electromagnetic fields are forced into a quantum. And that is the origin of the theory of quantum mechanics in 1925. So there have been many such things. And right now, some scientists like to complain. But right now, I think we're in the happiest of all situations. And that in many decades or centuries, people will look back at this saying, if only I were a physicist then. Because right now we have these two huge bodies of knowledge, quantum field theory, which was the synthesis of all that went behind it, and general relativity, which is the synthesis of all that went behind it. And they are in stark contradiction on several fronts, which I will explain. And so sometimes it's frustrating. This contradiction has been sitting there in one form or another for 50 years, but eventually we'll get through it. So let me explain what these two theories are, and when we do, it's going to be very, very exciting. When we do, okay, so what are these two theories? So I'm giving you one transparency on general relativity. Sometimes I teach a whole course on it. Quantum mechanics is usually 3 or 4 courses. You'll get one transparency on that too. Don't show these to anybody in graduate school of physics. Okay. So, sorry, that's quantum mechanics. I'm going to get back to general relativity. Okay, so what Einstein taught us is that space is curved. And if you have something moving in a straight line in a curved space, like the Earth going around the sun, it seems like it's going a circle. And if you work out the mathematics of that very carefully, as Einstein did, that simple hypothesis that space is curved, together with an equation which explains how it's curved, completely supplants the need for a separate force of gravity. It's just space is curved and everything is moving around in straight lines in curved space. What about quantum mechanics? Well, the uncertainty principle of quantum mechanics tells us that position and velocity are not simultaneously physically observable objects. It's only some combination of them that makes any sense. And in fact, positions and velocities, if you try to take them separately, are a little bit uncertain. Even though it may look like I'm standing motionless on the stage, in fact, the uncertainty principle of quantum mechanics says that my position must be subject to a very tiny, for large things, uncertainty. For smaller things, this uncertainty becomes more important, but for large things, it's very small. Now, here we come. So that was general relativity. And the next one was quantum mechanics. And now you want to put them together. So in general relativity, space is the dynamical quantity. Now, just as I said, it's not possible to say exactly where I am in quantum mechanics. In general relativity, it's not possible to say exactly where space is. Now, if that sentence didn't make any sense, it doesn't make any sense to anybody in the world. Nobody's figured out how to make sense of what it means to have a space-time which is subject to an uncertainty principle. But we have to make sense of it because we know that quantum mechanics is part of our world, and we know that Einstein's theory of general relativity is part of our world. And before quantum mechanics and general relativity, space was the blackboard on which all the laws of physics were carefully written. And now the blackboard itself has become part of the game, and it's become fuzzy, and we're just not too sure what to do. It's like the rug has been pulled out from under our feet. Now, that was a rather abstract way of saying what the problem was. But that abstraction translates into real mathematical puzzles that you can write down on a piece of paper and get your hands dirty with. So there's a machinery called quantum field theory, which for all the forces except gravity has done a stunningly spectacular job in making the classical forces compatible with quantum mechanics. It's called quantum field theory. I would say that it might be fair to say that it's been the main understanding. Quantum field theory has been the main occupation of fundamental theoretical physicists for the last century. There have been 43 Nobel Prizes for little pieces of solving this problem. It's been spectacularly verified. It's the most accurately verified theory in the history of human thought. It's been verified to 16 decimal places, this method of putting together quantum mechanics with classical forces. And despite this spectacular success with all the forces, the strong, the weak, and the electromagnetic, except gravity, when you try to use the same methodology for gravity, you get nonsense. And this problem is more than half a century old. Pauli noticed this all the way back in the 1950s, that any standard method of putting together quantum mechanics with general relativity was doomed to failure, but it was a very technical kind of failure. Now, over the last several decades, there's been a modification of quantum field theory called string theory, which does put them together in a harmonious way, but we don't know if this sort of string attachment to quantum field theory was ordered by nature or not. So it still remains an unsolved problem. And as Marco said in the introduction, the laws of physics as we know them, as we teach them at Harvard, are not mutually consistent. Now, there's another more physical form of this clash between quantum mechanics and general relativity, and that was pointed out in his most famous work by Stephen Hawking in a paper in the early 70s about what happens when quantum mechanics meets a black hole. Something really weird happens when quantum mechanics meets a black hole. So, but first I have to tell you what a black hole is. So, if you're on the moon and you can jump hard enough, fast enough, so that you get up to 2 kilometers per hour, you can escape the gravitational pull of the moon and continue forever out into outer space. On Earth, it's a lot. Did I say 2 kilometers per second? On Earth, it's a lot more because the Earth is bigger and more massive. You have to get up to 11 kilometers per second. Now, if you have a big enough object, the escape velocity can actually reach the speed of light. And if you have an object that is that massive, then light can't get out. And since nothing can go faster than light, that means that nothing can get out. So a black hole is a region of space-time in which the force of gravity has become so strong that nothing can get out, not even light. And this sounds very strange, but there are millions of these things. If you walk out the door there and look up at the sky, there are millions of them up there. We're orbiting around one as we speak in the middle of our galaxy. So these very strange objects are everywhere, and we don't know what they're up to. Now, the black hole has a really kind of fantastic history. Einstein wrote down his field equations in 1915, and they were so complicated that he predicted, at least the story goes, that nobody would ever be able to find an exact solution of these equations. A few months later, Karl Schwarzschild, who was fighting out on the German front, World War I, found an exact solution which described a black hole, and sadly died a few months later of pemphigus. He'd contracted out there. But even though, usually in physics, if you have an equation, you solve it, you're done. That's the hard part. This was the opposite. This solution was found 100 years ago, and people could not understand what it meant. And people have said the strangest thing, including Einstein himself, who wrote a paper in 1939 saying that black holes didn't exist and giving a reason that would certainly flunk him out of any reasonable general relativity course for having uttered such words. So it was even the smartest people around could not understand what this solution meant. And it took theoretical physicists working very hard for 60 years to understand, before you threw in quantum mechanics, what a black hole was. And many, they were so weird, many people refused to believe they exist, but now we know that they're just everywhere. Now, the description of a black hole that comes from Schwarzschild's solution of Einstein equation is, it's a really empty hole in space. And when I say empty, I mean empty. It's not like there's nothing here. There's air here. But I go into outer space, there's not even air, but there's still a vacuum. And the vacuum is actually a very rich place. A black hole, the edge of a black hole, is a place where space-time itself ends. There's nothing, less than, even more nothing. It's so nothing that it's hard to think about how nothing it is. And not only that, from the outside, all black holes look the same. They don't wear clothes and have different shapes, and the matter collapses and it drops down a hole, and this hole has no distinguishing features of it, or so it was claimed. And the famous physicist John Wheeler coined the phrase, black holes have no hair, meaning that all black holes look exactly the same. They're just round, empty holes. You might characterize them, as we'll discuss later, not just by the size of the hole, but the hole can actually spin. Now, this is all before Stephen Hawking came along and before the black hole had met its destroyer, quantum mechanics. And Stephen Hawking showed that because of the uncertainty principle, that black holes aren't exactly black, that quantum processes allow them to slowly radiate light, and after an extraordinarily long length of time, they will actually just radiate all their energy away and disappear. And they radiate at a fixed temperature. And this temperature, it's called the Hawking temperature, and Stephen has had it inscribed on his headstone in Westminster Abbey. I consider it one of the several most important equations of 20th century physics. And it takes the form of what's called a thermodynamic law. It tells you how the temperature depends on the mass of the black hole. And thermodynamics was what most physicists did in the 19th century. They took pots of water or pots of lead, and they looked at how long it took to heat them up and how fast they cooled down. And if you had a hot pot of lead and you put it in contact with water, and how temperatures and pressures and volumes and all these things changed. And there was a huge subject, which still exists, called the laws of thermodynamics, which explained all this. And then in what I consider one of the most beautiful moments in the history of scientific thought, Boltzmann in the 19th century showed that all this business about how long it takes for water to freeze and how long it takes for it to vaporize and all that stuff could be explained by what then was considered an outrageous, beyond the fringe assumption that matter was made of fundamental constituents called molecules. And that the water was a pot of water was a big pot of molecules, and you could explain everything about how it behaved using statistics. It's much more likely to find all the molecules distributed around the pot of water than it is to suddenly find them all being at one edge. And the statistical reasoning gets very intricate and advanced, but eventually all the laws of physics, all the laws of thermodynamics were explained using mathematical, statistical, probabilistic reasoning applied to large collections, the large collections of molecules that comprise, we now know, of course, it wasn't an outrageous theory. We've seen molecules now. And everything about the behavior of materials can be explained by statistical reasoning applied to their fundamental constituents, molecules. Now, a key ingredient in this is something called entropy, which really is the same thing as information, and we can really think of it as gigabytes, something we're more familiar with. How many the gigabytes in your iPhone is just how many configurations there are of the little transistors, whatever, or that they make the iPhone up out of, and so the entropy is sort of the central ingredient of this, and it's the measure of the complexity of the system. Now, with really only a few lines of algebra, Hawking's formula for how they radiate, how black holes radiate, can be used to infer how much information you can store in a black hole, how many gigabytes of information you can store in a black hole. And there's a very famous formula for it, the Bekenstein-Hawking area entropy law. And it's a formula which, it's not a formula in some sub-discipline of physics. It's a formula which ties together many of the discipline of physics. It involves the entropy or the gigabytes, which is information theory or statistical mechanics, the area of the exterior of the black hole, which is known as the horizon, so general relativity, Newton's constant, gravity. It involves Planck's constant for quantum mechanics. So it's a very central formula. And unlike, I've never heard anything can be questioned, but Hawking's argument for this formula depended on so little, even though it hasn't been directly measured. We're still many orders of magnitude away from the kind of experiment we would need to do in order to measure this formula directly. I've never heard anybody question it, not that it shouldn't be questioned, but I've never, because the derivation is so kind of breathtakingly simple. And it's a huge amount of information. So if you took all the data banks at Google, you could fit them all inside a black hole, a trillionth of a millimeter across. That's how good black holes are at storing information, how much stuff there is inside there. There's really a lot of stuff inside a black hole. Now, there's something called Moore's law, which you may have heard of, that every 3 years, if you take a computer chip that's a millimeter across, every 3 years, technology will keep improving, and you'll be able to double the amount of information you can store without increasing the size of the computer chip. And this has worked remarkably well, but if we keep it up for 300 years, if we keep doubling every 3 years for 300 years, we'll reach a bound, the black hole bound. And at that point, all of our computers will have to be made out of black holes, and we won't be able to do any better, because we think that it's a fundamental law of nature that nobody can do better than a black hole, that is the maximum amount. You can quickly arrive at a mathematical contradiction if you assume the existence of a computer that can store information, a larger amount of information than a black hole, in the same region of space-time. Okay, so if you've been listening carefully, you may have noticed that I told you two things which were completely opposite. One is that black holes are extremely complex, that came out of Hawking's work, that they're extremely complex objects that store enormous amounts of information. And the other is that there's just nothing there, that it's empty space. Furthermore, there's nothing on the boundary of it, and it would seem like it couldn't store any information at all. It's as if somebody gave you an iPhone and you started putting photos on it that were 4 gigabytes apiece. You put 16 photos in, and you say, aha, my iPhone can store 64 gigabytes. And then you tried to open it up, and you found out it was empty. So the problem is, in fact, so far, we haven't had all the tools we need, all the mathematical tools that we need, or experimental tools that we need to see what is really inside a black hole. And we don't know. Hawking inferred, much like the person who trying to figure out how many gigabytes in their iPhone by putting photos in, he inferred indirectly how much their storage capacity it had to have, but he didn't tell us anything about how the information was stored, much less how you get it in or out. Now, at this point, so that problem sat there for a quarter of a century. And at this point, and many people argued, including Hawking, that in fact the information wasn't stored, that it disappeared, that information was destroyed in our universe. But that eventually became an unpalatable point of view and couldn't be made. No consistent framework could still be true. We haven't gotten to the end of this story. But it looks very hard to have a theory in which information can be lost or destroyed, because it's tantamount to not really having any laws of physics. And how can you be a physicist and explain things without laws? So we didn't know what to do about that. Then string theory came along. And in string theory, we have a lot more tools. So string theory, I'm not going to tell you very much about it. I do give other public lectures on string theory. Not this one. I only have about 45 minutes. But it's a theory which does consistently put together quantum mechanics and general relativity. We don't know what, if anything, it has to do with the real world. But we know that it's a theory with black holes and quantum mechanics. And it's a theory which is very precise. And we have a lot of equations and a lot of tools that we can use that are not available for describing black holes in our own universe. Because in our own universe, there's so many things we don't know. You know, we just learned about the Higgs boson. We don't know what comes after the Higgs. We don't really know what makes up our own universe. But in string theory, we have some very complete description. So we managed to use string theory. And what we found in string theory was that the information is stored, that there's a kind of hologram that lives on the outside of the black hole. And that hologram stores all the information. And there's an alternate description of the black hole, which is complete. So it's familiar. My glass of water here, we could describe it as either half empty or half full. It's obvious to everyone that those are equivalent descriptions of the same thing. In mathematics and in physics, there are often equivalent descriptions, which it takes a very, very long time to understand that they're equivalent. And that's what happened here. The description, and I'll make it a little less than half full. The description of a black hole as empty and the description of it as full of all kinds of stuff were equivalent descriptions which just started from different points of view. And we were able to show explicitly that if you worked carefully, you would get exactly the same answer, no matter which point of view you started out from. And I want to say, because it'll come up later, something that was very important is that there's an extra symmetry involved. And physicists love symmetries because with symmetries, they can calculate lots of things that they couldn't otherwise using symmetry principles. And it was so-called conformal symmetry. I'm not going to explain what it is, but it's a big symmetry group. And we used it as a tool to compute what was inside. We discovered that the black hole had this symmetry, and we used it as a tool to describe what was inside it. Now, this is certainly progress, but we're not satisfied by understanding how string-theoretic black holes store information. We want to know how the ones that are up there in the sky staring down at us, the ones that Gabriella saw that ran into each other 1 billion years ago, we want to know how they do the trick. We don't want to assume anything about string theory. We want to understand real black holes in the real world. But it might be true that some of the tricks that string theory used, that some pieces, in particular the conformal symmetry, we might be able to see parts of them at work in the real world. And in fact, we have made some encouraging but not complete progress in that direction. So the first thing we started to think about is a so-called extreme Kerr black hole. So as I said, black holes are characterized by a total mass or size. It's the same thing. But also they can spin. But one of the things that was shown in 1963, 50 years after Schwarzschild, somebody found Roy Kerr found the spinning black hole solution, and he found that they can't spin as fast as they want. A black hole can only spin so that its horizon is moving at the speed of light. Can't go any faster. And these ones where the horizon is moving around at the speed of light sounds like they might be more complicated, but in fact they're more simple, because it turns out for things to move at the speed of light is very difficult, and so there are many fewer possibilities, and special tools emerge that enable you to analyze them. Not only that, a disproportionate number of them have been seen in the sky. For some reason which astronomers don't understand, black holes like to spin really fast. And of the supermassive black holes, something like 80% of them, they did a series, are spinning within 10% of the speed of light. So most of them, the spin hasn't been measured, but many of them are going, and I list a few here, are going within 1% or 2%, more, almost at light speed. So these are very physical objects. Here's a picture of a black hole, and how if you don't have a gravitational wave detector, how you can see it just using electromagnetic emissions. Typically, there'll be some companion object, which is feeding matter, which forms what's called an accretion disk, and swirls around and eventually falls into the black hole, which is in the middle here. And for reasons which we still don't fully understand, many of these black holes like to spout the matter that didn't fall into the black hole in jets aligned with the spin coming out of the horizon. Now, I have there's a special place that we're interested in. The horizon of the black hole is right here. And that's the interesting place. That's where we found the hologram in string theory. And I was very struck when I was watching Gabriella's simulations the other day that she had two black holes dancing around. There was a lot of complicated stuff in space. And then all of a sudden they emerge. And when they merge, all of a sudden everything becomes simple. And that point where they merge, right at the horizon there, is the interesting point for theoretical physicists to study. And I have an animation that NASA made here of GRS 1915, where, like Gabriella did, they turned the electromagnetic into sound. And we're zooming into the center of the black hole. And what we want to understand, because it's where the information is hopefully stored, is that little bit right at the edge there, right at the edge of the black hole. So right at the edge of that black hole, we've shown that the Einstein equations by themselves, when the black hole is spinning at light, we've shown that the Einstein equations by themselves imply the emergence of this conformal symmetry, which suddenly enables you to do all kinds of computations that you couldn't do otherwise. And indeed, we found, we gave some evidence that there is also a hologram around these rapidly spinning black holes that stores the information about what goes on inside a black hole. Now, what observational signals we'd like to connect this in some way, if we can, with experiment. And what are the observational signals of extreme Kerr conformal symmetry? Well, there's something called the Event Horizon Telescope, which is they keep delaying, as all experiments are wont to, but they hope to release their data in January. And it turns out that if you take all the radio telescopes on Earth, or all the good ones, and you all the best ones, and you synchronize them, you can make a telescope. You need a big telescope to see a small thing. And the biggest black hole in the sky, there's two of them. One of them is Sagittarius A star, which is the big black hole at the center of our galaxy. And it is the size in the sky, takes up the same solid angle in the sky as an orange on the moon. It's really small. And no astronomer has ever resolved an image that small. They've resolved things maybe 100 or 1,000 times that size, but nothing that small. This Event Horizon Telescope, by stringing together all the telescopes on Earth and synchronizing them, is going to be releasing data hopefully in January, certainly within the next year. You'll certainly be seeing it on the news. They're going to get 20 pixels, they hope, on Sagittarius A star, which is the black hole in the center of our galaxy. And then there's another, I think, even more interesting black hole at the center of the galaxy M87, which is 1,000 times bigger than Sagittarius A star. I think Sagittarius A star is around 1 million miles across. This one is 1 billion miles across, but it's also 1,000 times further, so it looks like the same size. So they're going to see these two black holes. They've taken the images, they're just processing them now. And so we're really entering a new era in science. So black holes are becoming important in many different ways. They're becoming important to people like me because they lie at the center of those things about the world that we don't understand. And they're becoming important to astronomers because all of a sudden, as astronomers have been making one amazing advance after another and seeing the sky with greater and greater precision, all of a sudden, we've reached the threshold where we can actually see in some detail a black hole in the sky. So this is a very exciting thing. Here's a picture of this is in the Atacama Desert, the so-called ALMA telescope, one of the radio telescopes that's going to be used to see M87. I think this one is up at 10,000 feet. And there are a half dozen more, and they synchronize them. And by synchronizing, just as Gabriella explained, they only had 2 or 3. The Event Horizon Telescope has about 7. They're looking at very different kinds of things. They're looking at electromagnetic emission. The LIGO is looking at gravity wave emission. But presumably someday they'll also be coordinating. Here's an artist's rendition of the black hole M87 sitting at the middle of an accretion disk, and it has a very prominent jet, which has already been seen. And so what do we expect to see? So that's where conformal symmetry comes in. We can use conformal symmetry to predict what will be seen by the Event Horizon Telescope at M87. And we've done that, and it's submitted for publication. And here is a picture of our predicted, these lines. The Event Horizon Telescope is not only going to see the luminosity as a function of position on the black hole, but they're going to see the polarization. And what I've drawn here is the picture for what the polarization looks like. So we're hoping that they'll be able to see that. Even if they don't, it's going to be an exciting experiment. Okay, but that's just for black holes
that are spinning very rapidly. Those are the ones, of the ones that we can see, these are the ones that we understand the best, but we want to understand all of them. And it's kind of weird to only understand some limit. We want to understand everything about black holes. And so this is work I've been doing with Stephen Hawking and Malcolm Perry, and more recently Malcolm's student, Sasha Heiko, over the last 3 years. We've discovered that there was a very subtle mistake in John Wheeler's assertion that black holes have no hair. It wasn't a mathematical mistake. There is a mathematical theorem that is correct. There's a question of what it means for two black holes to be different. And this goes back to Einstein's equivalence principle. And Einstein, the basis on which he built the theory of general relativity was the equivalence principle. And the equivalence principle says that there should be no difference, no detectable difference between being in an elevator, which is falling in a gravitational field like the Earth, so you don't feel any gravitational force, or being in an inertial elevator out in outer space. True statement, very subtle one to state precisely mathematically. And it turns out when the space-time has edges, like the edge at infinity or the edge of black hole, there's some important subtleties in how to interpret that equation properly. And we've unraveled those and shown that, in fact, it's not true that all black holes are equivalent, that they do have some structure on this horizon. And this structure, which we discovered in this completely different way, is very much like the structure that was encountered in string theory. And in what will be Stephen's last paper that we just posted 3 weeks ago, we found some evidence for this conformal symmetry in all black holes. And we don't have a proof yet that works this way, but we're all feeling optimistic. And as Stephen said, like to say, watch this space. Now, I have to say that giving a public lecture like this, it's a little bit like you went out to the Grand Canyon. Imagine you discover the Grand Canyon. And then you see it, it's so beautiful and everything like that. And then you don't have a camera or anything, and then you come back and somebody asks you, tell me what it's like. In words. Very hard to describe. And the thing that's wonderful about all of this, to those of us who work on it, the thing that's wonderful about it, it's all in the equations. To us, the thing that gets exciting is the equations and the way it all fits together so beautifully and intricately. And I'm afraid I've made it sound as if it's some simple thing that can be explained by some stick figures. But in fact, there's very precise mathematics behind all of it. And that is what gets us excited. And so in conclusion, we don't know how things are going to work out. String theory looks interesting. We don't know what it has to do with anything. Black holes are there. There's clearly very exciting, and there's a lot of interesting things to do, and we don't really know what lies on the road ahead. So thank you very much.
So, thank you very much, Andrew, for this.
Thank you.
Please take a seat. We will have now a discussion. Before I invite the second person for this discussion on stage, let me just remind you that you can ask your questions both in French and English. They will be translated also to Andrew. And you can ask them live. There will be microphones on the aisles and through Twitter. So don't hesitate if you don't get the mic in your hands or you're raising your hands too many times. Write a question on Twitter and they will be relayed on stage with me. Please, take a seat.
Where should I sit then?
Let's sit here. And then for this discussion, we'll also have last evening's speaker, and that is Gabriela Gonzalez, who I invite on stage with me. Thank you. Okay, Gabriela. So you were part of this group, huge group, that discovered in 2015 the first proof that the so-called gravitational wave were real, and they appeared by the merging of two black holes, and the merging of two black holes created those vibrations on the fabric of space and time. That's what we describe it with. How do your work relate to what Andrew is doing? Is that maybe a tool to maybe prove or show something of what he's working on?
Yes, absolutely. Of course, we need predictions first to test, but this structure, knowing about the structure of a black hole horizon, might influence the waveforms that are produced when the black holes merge, the properties of the final black hole. That all needs to be studied. Of course, the effects are very, very subtle. The black holes that we see are not that big. I mean, we say they're big, but they're not millions or billions of solar masses like the ones that the Event Horizon Telescope will do. But this is what science is about, is having theories, very exciting theories, that make predictions that are beautiful, and then having experiments, observations that test those theories.
Andrew, you mentioned briefly this paper that you just published actually 2 weeks ago with Stephen Hawking, the late Stephen Hawking. And the New York Times put it really nicely by saying that Stephen Hawking was kind of speaking out of the grave with this paper that you co-signed. So what did he say? What would he say if asked what the importance of this paper was? I mean, you saw him, you talked to him so many times. Can you tell us a bit more than just the physics that's in the paper?
Well, he was. Oh, I have a mic. Yes. Stephen was never did anything half-heartedly. He was an enthusiast. He felt we had solved the problem and that it was only a matter of time before we got it all to come into place. And he was extremely excited about all of it. When we first started the ideas of how this might work out, we were up until very late in the night, and his nurses said they hadn't seen him that excited in 40 years since and he also, it was very moving in the last few months of his life. He was very ill, but nothing brought him more to life than talking about physics. And his last correspondence was at his funeral. We had a phone conversation with him, and at that point he was unable even to write on his screen, and we were just reporting this was 3-4 days before he passed, and his nurses said he had gotten a huge smile on his face hearing about the progress we were made. And that was his last expression.
And how would you consider this paper? Is that the start of the first maybe step to a proof of something for this marriage between the two big fields of physics?
Well, different physicists have different personalities. And for me, it's a little bit like being a gambler in Vegas or something. You can't get too upset when the chips are low, and you can't get too excited when the chips are high. You have to keep your cool. So many times I've been very excited about ideas which have turned out to be wrong. And I've also been excited about ideas and I would say, I think Marcos would agree with me. If 1 out of 10 of your ideas turns out to be right as a theorist, you're doing really, really well.
Good ratio.
So you have to kind of, protect yourself against overexcitement. So I'm still in the wait and see. Stephen was beyond the wait and see. I'm still in the wait and see. I'm sure that we've made some progress in the last decades. I'm sure that I'm not waiting and seeing about that anymore. But whether this last bit, whether what Stephen and Malcolm and I put together, whether that's everything that we need, or whether there's still big significant chunks, or whether that's even a piece of it, I'm not personally letting my guard down.
Maybe one last question.
You probably had that problem at LIGO too.
Yeah.
We did like you are doing, a piece at a time. Never getting too excited, but always counting on reaching the end.
In fact, I had a conversation with Ray Weiss about this the day after.
Ray White's colleague of
yeah. And he said, oh, it's not like that. It's just about whether the detector is working or not. That's what keeps me going every day. Whether there's mice in it. Get those mice out, And then all of a sudden he gets a Nobel Prize. He kept enough mice out, and that's a Nobel Prize.
The mice were around the vacuum tubes, not in the detector, but still, yes, they were very annoying.
So one last question before I go to the room. You mentioned many times black holes, and you mentioned our black holes in the center of the galaxy. You mentioned the event horizon, but you didn't mention the gravity experiment in Chile, which actually last summer discovered that, amongst many discoveries, but one is important, is that some stuff around our black hole is spinning at a speed of 30% of the speed of light, which could be the first hints or the first proof that there actually is a black hole inside our galaxy. So what is for you the importance of this result from gravity?
Well, you connect what you can, and not everything can be connected. And we're very happy now that we've found some kind of connection between the rapidly spinning black holes and the ideas about how the quantum puzzles of black holes can be. People make predictions, theorists make predictions for experiment, and 999 out of 1,000 are wrong. I think our paper odds are better than that. I won't say how much better, but it's not 50-50. And some things you can connect, and the nature of science is you just keep pushing forward on whatever front that you can push forward to. And it doesn't seem to be, especially with this recent hotspot they've seen, it's kind of looking like Sagittarius A star in contrast to M87. M87 astronomers have claimed is going at 1% of light speed. and Sagittarius A star probably isn't spinning that fast, and we don't have a prediction for that. So it's not going to be, of course I love reading about all this, but it's not going to directly tie into.
And you also mentioned this first picture. So what do we have to imagine? It's going to be published all over the world in newspapers or etc. What shall we imagine, the first picture of a black hole? Is that something like in the movie Interstellar that we saw a few years ago?
No, it's going to be, you know, I see Shep Dollman, the head of it, once or twice a week. You know, they're not telling us what's there until they release it. And, but it's not going to be, you know, they were hoping for, if everything goes well, they were hoping for 20 pixels, and that will be 20 numbers, you know, 4 by 5 or whatever it is. That will be 20 numbers, and there'll be an arrow in each one. So if those arrows line up with the arrows in my diagram, I will be so ecstatic.
Okay, we have many time now to open the room for questions, so please raise your hands. There is one here, one here. So I'll start right here in the middle, au milieu.
Thank you. I have a simple question. How does matter energy curve or bend or distort space-time?
How does matter distort space-time? Well, that is what Einstein's theory predicts and has been measured. Our gravitational waves are the tiniest distortion, but there have been bigger distortions of space-time that are the cause of gravity. The motion of the Earth around the Sun is also explained by the curvature of space-time. Of course, it's also explained by Newton, but there are many other predictions of Einstein's theory of relativity about the curvature of space-time. The first one that was proven was that light bends when it goes near the Sun. And that has been proven not just with that eclipse in 1919, but with many, many other much, much better measurements since then. So how does it do? Well, you have to solve Einstein's equations. Those are not easy. But that matter bends space-time, there's no doubt about that.
There was one.
But Einstein said that. But how does he or anybody else explain why matter energy curve or bends of the space-time?
Okay, you just hand it to me for a second.
You have one.
That's a question for philosophers. Sitting over there. Physicists answer what?
There is one.
Why is for philosophers?
Il y avait une question au premier rang ici. Monsieur, oui.
Question in the first row. Gentleman in the first row.
I had read that Stephen Hawking, in one of his last papers, I don't know if it refers to one in which you were working with him in May, had basically affirmed or decided that it was true that there was a multiverse, that there were parallel universes, and that using quantum theory, he began to simply discuss not that the legitimacy of there being parallel universes, but that because of quantum theory and that the date of the beginning of the universe appears to be 13.7 billion years, that therefore, mathematically, the amount of parallel universes possible is contained. I was surprised for two reasons. One is it true that he sort of has come to the conclusion, or that he feels that there are parallel universes, and then using quantum theory, is he calculating that there cannot be an unlimited number. Was my understanding correct?
Well, that paper, it is true that Hawking likes the idea of multiverses. I don't. Not all physicists do. I think among working theoretical physicists, my view is more common than Hawking's, but nobody really knows. And that's why I don't like it, because nobody knows, and how do you figure it out? If there are other universes, you can't see them, then they'd be part of our universe if you could see them. That paper had a number of assumptions in it, and I don't think that Hawking himself, were he alive, would assert that that's a definite prediction. It's a prediction which follows from some assumptions which he couldn't be very, very confident about.
But isn't it in string theory? You mentioned string theory. Is the existence of multiverse not included? Could it be included in string theory?
It could be included in string theory, but it's not obligatory in string theory. And string theory really has very little to say about whether or not there are multiverses.
Monsieur?
Gentleman over there.
Thank you. Please, I would like to know if there is an alternative theory that could explain that something can go faster than the light. Because it's always the limit, the speed of light. But are there other theory that can show maybe that there is a faster speed of light?
Well, there are many theories. So I guess, is there a theory that assumes there are speeds faster than light? I'm sure there are. Whether they have predictions that can be proven, that I know that there aren't any predictions with theories like that. And again, I'm an experimentalist, so I look at observations, not so much theories, but predictions made by theories. However, that the speed of light is the maximum speed of light is not just an assumption in the general theory of relativity. It's a consequence of the special theory of relativity, which is something that's much, much more commonly accepted and proved and used in all of physics, not just in relativity, but in particle physics.
I may have a related question to you, Andrew. You mentioned in your paper that I read it, but I didn't understand it, but I read it. At the very end, at the conclusion, you mentioned that it's just an incremental evidence, and you also said that it's going to be a task left for further generations to build on your work and on Hawking's work. I'd like you to comment again. Yeah. I'd like to comment again.
There's no generations in there. I'm hard at work on this myself. I'm not leaving it to my kids.
No, I'd like you to comment on the pace. You mentioned that it's going to be with us for years or decades or centuries until we find maybe the solution. Or is that something that we could find around the corner?
I think I just said left it for future work without a time scale. I'd like to solve it tomorrow.
Yeah.
We never know how long these things take. And that's one of the, even LIGO, they didn't know what was out there. And they didn't know, it could have been that they waited a year, 2 years, for 5 years, they had to wait for advanced LIGO, then they saw some neutron star. It could have been many decades before the point that we're at now. But now we're there, and we're going to be even further soon. So both experimental and theoretical, it's just, there's no predicting how fast it will go. But at the same time, I would like to say that this problem of putting together quantum mechanics and gravity is a problem of historic proportions, and that I find myself irritated at grant personnel who want you to explain that how you're going to solve the problem in the next 3 years. That we should, that this is a problem which may take a long time, but not necessarily that will. And LIGO, I mean, that Ray started on that in 1967. That was 50 years ago. And the problem of understanding what a black hole is, just classically, that was 60 years. And now we're on to the quantum part of that. That's been ongoing for 40, 50 years. So these problems can take a long time, but there can also be sudden progress in there.
Gabriela, you were actually testing the machine when you found the waves. Were you ready also to work for decades before finding them?
Well, what we were counting on were the predictions for how often we would be able to detect mergers of neutron stars, because there were several binary neutron star systems known in the galaxy, so we could have astronomers extrapolated those, and they only had an order of magnitude error in those predictions. So we knew with some certainty that in a few years, when we got the detectors working at the sensitivity we wanted, we had a reasonable chance of discovering those. But the universe turned out to be full of black holes.
I can attest, I was on a TV panel with Gabriela about 6 months before their discovery. And I can attest to her optimism about something happening very soon. Yeah. I think it was better than you thought, though.
There was a question, yes, here in the front. Thierry, juste derrière vous. Et après...
Thierry, just behind you, and then on Twitter.
Question or not, but it doesn't start with why, it starts with what. So I would be curious to know what is, according to Professor Strominger, a beautiful equation. Is the beauty in the simplicity of the equation, in the simplicity of the derivation? Is it the amount of things that it can describe? What makes an equation beautiful?
Well, that's like asking what's a beautiful painting. You know it when you see it, but I can't articulate it.
There's one question on Twitter which asks whether what you've done recently has anything to do with time reversibility, and if so, what does it say about it?
About time reversibility. So,
when you speak about entropy, you speak about...
Yes. Time reversibility is... There's some understanding of it in physics. There's some understanding of why entropy increases, both the second law of thermodynamics. But I feel that it's fundamentally mysterious and one of the questions that we don't understand. I mean, in fact, in a way, it was on my second transparency. Why was there a Big Bang? Why? Well, okay, now I'm being a philosopher. I certainly black holes are very complicit in making time irreversibility hard to understand, because there's singularities you can fall into a black hole, and despite what you saw in the fourth Starship movie in the beginning, you can't come out of a black hole. So there are no black holes in the past. They're all in the future. They form by collapsing stars, so they're there at the end of the universe, if they haven't evaporated, until they evaporate. But they weren't there at the beginning of the universe. And we don't really understand that. So I don't think we've shed much light on this, though I think when we get through this, that will be a question which will be more on the forefront than it is now. I don't think that that is a question which is infinitely far away.
I have a follow-up on this, actually. I talked quite a lot to Thibaut Damour, who was here on Monday,
Yes.
in interviews as well. And once he said to me, well, the most advanced theories, like string theories, may be actually too rich for the human mind to understand. So will human intelligence, will it be able to understand the problems that you're facing? Or maybe because we're talking so much of artificial intelligence at the moment, will we need maybe something to help us to solve your problems?
Well, anything's possible. Obviously, I'm proceeding under the assumption that human intelligence is enough to tackle these problems.
Okay.
I think that we need help, and we use help already, right? We know how to write Einstein's equations. We know how to calculate with pen and paper a few solutions, but to do the solutions of complicated or even some simple problems like a collision of black holes, you need the help of computers. So I think that human intelligence is extended with the tools that human intelligence creates. So we explode, we expand our intelligence. And whether there's a limit to that, that's a philosophical question.
So I will take one very last question. Is there one? Yes, here, because time is running really fast.
My question is going to be in French.
Yeah.
Since black holes have different sizes and masses, I suppose that they can also have different densities. Does that mean that each black hole has its own structure and that each black hole will be different from the next one?
Did you get it?
Yeah, I think I got the question. So that is one of the peculiar things about black holes, which is that it was believed and is still believed to be true in some more subtle sense that you make a black hole. Doesn't matter whether you run cars into each other, planets, stars, that the so-called no-hair theorem, the statement of John Wheeler that black holes have no hair, implied that a black hole is characterized just by its total size. When you first make it, of course, if you look, this was very beautifully illustrated in Gabriella's graphics. It's made in a very complicated way, but all of a sudden you see this zap in a very short time into this round thing with no character. There's all kinds of characteristics before of their motion and the curvature of space around them, but once you make it, it just kind of zaps into this round shape, and all the regularities are quickly radiated off to infinity. And so it was thought that the black holes are just, and in fact, the one that she was illustrating was in fact spinning, not very rapidly, only at, I think, what is it, 7/10 the speed of light? Yeah, something like 7/10 the speed of light. And you couldn't see that spinning on the...
In the movie, yes.
In the movie, you can't see that spinning because it's sort of spinning in place. But it was thought that within an extraordinarily short time, no matter how you made a black hole, it settled down to a unique object, a unique hairless object. And what we've learned in the past few years is that you have to be very there's a subtlety in the way that you describe the way the edge of the black hole is tied into the rest of the space-time. And that is where the information about what went into the black hole has a resting place.
So it's now time to come to an end. As usual, you know that I will leave you with a quote. No surprise today, it's going to be from Einstein, but it's a kind of contre-pied. Einstein said this: "It would be possible to describe everything scientifically, but it would make no sense. It would be without meaning, as if you described a Beethoven symphony as a variation of wave pressure." What does inspire you? What does inspire you?
It's true. There's much more out there besides what we do.
Gabriela?
I love explanations. I love all explanations and looking for those. And I don't like that quote.
Okay.
I don't have to like everything about Einstein.
Thank you very much to our two speakers tonight. And please, s'il vous plaît, encore 2 minutes.
Please, 2 minutes more of your attention. I give the floor to Mr. Courvoisier, the president of the Wright Foundation, for one last word. Thanks to all of you for still being here. Thanks for your attentive listening during the week. You've contributed to the success of this week. But I would also like to thank very warmly all our speakers, those who enabled us to acquire many, many new forms of knowledge. Thanks to all my colleagues in Geneva and in Bern who introduced them and who connected the work that they are doing and the work that our speakers are doing at home. And this link is particularly important to me. Thanks to Olivier for having been the MC of these evenings with a lot of success and great energy. Thanks to all contributors to ScienceScope, the experiments that you've seen outside of this room and who enabled you to visualize some biological and physical effects of gravitation. Thanks to the interpreters who've been helping us during the week. Thanks to the security staff and the hostesses who went around with the microphones. It's very important for us to have a system that works properly with the minimum of order. Entropy cannot be infinite in such a room. Thanks to the technician, to the technical team who worked on the lighting, on the web, on those who enabled us to receive the questions via Twitter, and thanks to all the technical staff that enables the broadcasting of these events. And finally, thanks very much to Fanon Sisban and Ascension Lozano, who were kind of conductors in this orchestra. They contributed to organizing this week, and they did a tremendous work without any problems or any tensions, and I think this is extremely remarkable. It means many, many people indeed. And that goes to show how difficult it is to organize a week like this one. I'm very, very happy that Geneva is able to set up such a series of events in order to share with you the results of modern science. Have a nice weekend and see you in 2 years' time.